Is this correct that the background is left-handed? It's just the wrong way around? Looks like it.
Can you repeat?
Pardon, please?
It looks like the background, you know, the picture you sent me is the wrong way around. Or does this only look like here on my screen, like that?
It's only visible in your screen. It's perfectly fine. We can see it perfectly.
Okay. And it's also the right way.
Yes, yes, reflection.
Like
it's the reflection, basically. It's perfectly fine.
Okay, thank you.
Sharmani, good afternoon.
Good afternoon.
Good afternoon, Mr. Suresh Sharma, Lieutenant General Suresh Sharma. Ji. Sir, good afternoon.
Good afternoon. सुनील जी कैसे हैं?
बस ठीक सर, आप सुनाइए सर.
Good. So we can wait for a while. I can see our speaker is already on the screen. So shall
Yes,
we
sir.
wait for another 4 or 5 minutes? I think people are still joining.
Yes, sir. Yes, sir. Yes,
In
sir.
the meanwhile, let me welcome our speaker for the day.
Yes, sir.
Mr. Zeidler, good afternoon.
Good afternoon, sir.
How are you?
Well, okay, thank you. I hope you are doing well as well.
Yes, all well here, and we've been fairly active, you know. I think if we look at ourselves in the last 6 months, in 1 week, we are doing almost 2 sessions these days. And and this week, we've had a meeting yesterday. In fact, we've had a long meeting, internal. We didn't have any international people. It was domestic, and it was on the automation. We had some very good speakers yesterday, and it was almost 2.5 hour session.
Wow.
So where are you based? You know, you are in London?
I'm actually I'm based in London, but currently I'm in Austria.
Okay.
That's where the home base is.
Yeah, which place in Austria?
In Salzburg. That's not far away from the German border.
Okay, you chosen the best place in Austria to live, you know, Salzburg. Beautiful, and it's so historical. In fact, I've been there. We've been there,
really?
and I was in. I went there in 2009. We were on a tour, and we were taken there. I think within, if you are going first time to Austria, one of the must-see places is Salzburg. It's so beautiful. It is so historical. We know that. Why is it so prominent?
Lots of mountains around. Yes.
Yes. Sunilji, as I understand, I think you said that good about 75 people are going to join, but I can only see. So are we going to wait for some more time? Shall we start now?
I think 5 minutes we can wait for.
Okay. Okay, we can wait.
Maybe people are still tired from yesterday, from the long session you had yesterday.
No, this is surprising, you know, when we tell more and more people that people must take the benefit of this lecture series. A lot of people show promise, you know, and when we carry out our estimates, we find that, okay, 50 people, 60 people are going to join, or maybe like today, the estimate was that at least 75 people are going to join. But when the time comes, I don't know, maybe a weekend, so people slowly start drifting. Ultimately, just half the number joins. And that is also a little late. That's been a trend that I'm seeing.
I understand there's a holiday on Monday as well.
India, we are observing a holiday on Monday.
Yes. So that's probably also one of the reasons why not many people are, not so many people are.
Yeah, some people, although pandemic situation is still bad, but then a lot of people are still traveling and holidaying. How's it in Austria now? I'm talking about the pandemic.
COVID, yes. We are not doing too bad, but the numbers are going up, unfortunately, because the government decided some time ago to open up basically everything. There's very, very minor restrictions anymore, and people are not acting very sensibly. And
that's across the globe now, you know. Maybe a stage has come that people care no more. Even in India, we have the same situation that we can't keep the things shut down. The moment you open up something, when you go out, you feel that there is hardly any restriction. Everybody is doing its business as usual. And you come inside and see the television news, or you get to hear from your friends and family, you get a little worried. So it's a very mixed kind of but then you are right. I think most of the people, especially the ones who now, the latest now, that if you are vaccinated, you feel that I got a license to move around now, which is not true. which is
Yep.
because a large number of vaccinated people are also getting through.
Oh yeah, oh yeah. I mean, fortunately, the percentage here of what they call a breakthrough, so when people are fully vaccinated and they still get infected, it's in the range of 1%, which is good. But still, it doesn't give you a free range for everything. You
Yeah.
still need to be reasonable. And I think we need to learn to live with this. That's what it's
Yeah,
the only
that's. I think sooner or later, you have to find your own ways and means.
Yeah.
Be a little more sensible. No, it can't be what it used to be 3 years back or 2 years back.
Yeah.
But then it can't be shut forever also. I think
No.
we have to learn to live with it, to find our own ways and means to deal with it.
Yes, we have to live with it. It's like with the flu, a virus, we need to live as well. And there are vaccinations, there are treatments, there are certainly people also dying on the flu, but it's something which will become our part of our daily life.
Eventually, yes.
Sir, I think now we will start, sir.
Yeah, let's start. Others, people are coming in, but I think I will need 4 or 5 minutes to introduce. Right, ladies and gentlemen, good afternoon to all of you. Before I start, once again, I would, expect and request all of you, wherever you are across the globe, please be careful. Pandemic situation is not yet over. Vaccinations are well under the way, but still there are breakthrough infections, and mostly it happens wherever there have been some letdown. So keep your guard up, keep yourself safe, keep yourself healthy. And those who are not yet vaccinated, our humble request to all of them is get vaccinated as early as possible. Right, ladies and gentlemen, now customary for me to introduce our 2 organizations which are responsible for conducting this kind of events. First is the Tunnelling Association of India, founded in the year 1976 under the aegis of Central Board of Irrigation and Power, and we still continue to be under them. And we are very closely associated and work under the umbrella of ITA, that is the International Tunnelling Association. We are the official representatives of India. Whenever there is a World Tunnel Congress, it's the TEI team along with some more associate members which goes there and participates. The aim of the TEI is multifold, but primarily it is to network, to provide a single platform in the country where all our people with the academic background, with the consultant background, with the builder's background, with the material supplier background, or with the equipment supplier background can come, or with the government officials can come and join to exchange ideas, to learn from each other, and also to find a common ground. We also conduct the World Tunnel Congress as and when it is allotted. In addition to that, every 2 years, we conduct Tunneling Asia, like the last one we conducted in February or March 2019 in Mumbai. This year, we could not do it because of the pandemic situation. We also have the young members, which is a separate chapter under the TEI, which was added in the 2018. And overall, we have more than 600 members and the numbers are growing. Along with us, we have a sister organization, which is the Center for Excellence for Tunnels at a government organization called the National Highway and Infrastructure Development Corporation Limited, which is a government body under the Ministry of Highways. They are also another platform for advancement of the tunnel development in India. So the 2 of us need to join together. And today is one such experiment where you can see that right on the top, it's written the Tunneling Association of India, along with the CETS, NHDCL is organizing the event today. Now, coming to the, ladies and gentlemen, this is being delivered by and sponsored by a company called Zeidler Consultants. Now, some of you will be a little, sort of concerned as to what is this name. This name is the 2 gentlemen, okay, the 2 partners, okay, Wojtek Gol and KurtZeidler. One of them is with us here today, right across. You can see him on the view foil. So the two together, Gall comes from one and the Zeidler comes from the other one, and they are the Gall-Zeidler Consultants. It is basically UK and US based firm, but it's got presence over almost the entire world now. In our part of the world, they are located in Singapore and in Delhi. In Delhi, specifically speaking, they have their presence in AeroCity area, and more about. Now, they're worldwide consultants in the field of geotechnics, tunnel design, tunnel engineering, tunnel construction supervision, and the project management. Basically concentrate on the tunneling. In addition to that, their expertise is also in the sector of transportation, in the infrastructure, water, mining, and all. But like I said, their focus still remains tunnels, and within the tunnels, they specialize whenever we are doing in the urban setting, where the overburden is shallow, and they have that specialization that because of the shallow overburden, not to disturb the structures which are in that zone, they have that area of specialization to undertake the tunneling works. They do the feasibility studies, they do the tunnel design, also do the contract documents right up to the bid stage. They do construction supervision or construction management, and also during construction design support. So all that which goes along with the tunnel, and they have a plethora of experience. If you see the number of projects that they have participated, some of the very, very complex projects they have participated. They have also got expertise of operating in the hydropower sectors. That is also to their today. So I'm not going to speak more about the company. So this is a very brief introduction for the company. Now let me introduce the speaker to you. Like I said, Mr. Zeidler, who's sitting, KurtZeidler, Dr. KurtZeidler, who's sitting right across us, is a renowned person in the field of tunneling. He's got more than 35 years of experience. He's a doctorate in the geology and engineering geology from the University of Salzburg, and he obtained his doctorate, the PhD, in the year 1987. He is member of large number of technical societies. He's experienced in geotechnical engineering, project management, design checks for the underground structures, for the slope stabilization in both and in rock. Now, like I said, okay, his area of expertise lies in the tunnels and the underground structures, both for tunnels, for underground structures, and the caverns. Now, ladies and gentlemen, I must also tell you that he is not only called an expert, but his services as an expert are utilized worldwide, both as an individual expert on the projects and also as an expert technical witness for the various arbitration cases. He's published a large number of technical publications. He's also, like today, he's now going to be talking to us. Similarly, he is very fond of delivering talks and lecturing on the subject of tunneling. He's an expert in the convention tunneling, in the TBM, and also in the cut and cover, and has got experience of dealing with hard rock, the mixed phase, and the soft soil conditions. So name a situation in the tunneling, I think he has faced it. He has that knowledge. Now coming to the subject of the day, ladies and gentlemen, he is going to be talking to us, as is there on the view file, on the Norwegian tunneling method. You are aware there are basically two basic, other than the TBM. When you look at it's either the Norwegian tunneling method or the new Austrian tunneling method. Both have got their own ways of doing more things. But when you look at the Norwegian tunneling method, you know that this was developed for the projects in the solid or the fractured hard rock primarily. And this is that for the last 60 years, they have the experience in the Scandinavia. But originally it was utilized for the hydropower tunnels, but gradually it has now come to the highway tunnels also and for the railway tunnels also. We know that it uses the shotcrete, that is the sprayed concrete, as the support along with the dowels. Now, those who deal with it, you know that there is something called the QSystem as to how do you classify a rock. I'm sure he's going to talk about the classification. How do you classify a rock and the QSystem of rock classification? Basically, that decides the rock mass, and that rock mass will decide as to what kind of support system you need, permanent support I'm going to in the manner of speaking. And this the rock classification, there are certain parameters which describe the condition of the rock mass, basically in the jointing and the joint conditions. Now, this entire methodology is updated from time to time. And today's workshop will focus on the fundamentals of the Norwegian tunneling method. At the end of the subject, he's also going to compare, draw a comparison between the Norwegian tunneling method and a very short comparison between this method and the other NATM also. So this much about the brief introduction. Now I will not be between you and the speaker. So over to Mr. KurtZeidler for delivering his talk. Dr. Zeidler, all yours now.
Thank you very much for the kind introduction, and I really appreciate that you have invited us to give this presentation here. I hope you can see my screen. As the introduction quite rightly said, we are focusing on the tunnel itself, basically building the tunnel, and that can be in hard rock as well as in soft soil. We're covering the whole range. Today, we will talk about the Norwegian tunneling method, and which was quite rightly said, was developed in a hard rock environment. Norway belongs to a very hard rock province, something which is in such a concentration only to be found in the Scandinavian area. Norway, Sweden, and these countries have a lot of this hard rock, and hence this tunneling method has been developed there. Just a very brief overview over the content of this presentation here. I will give a very brief history. I mean, the history is, we could talk about probably another 2 hours just about the history of Norwegian tunneling, but I will keep it very brief, and then I want to home in a little bit more on the fundamentals of the Norwegian tunneling. And I'm very careful calling it a Norwegian tunneling method, because it is like the NATM, not necessarily a method. It is an understanding of how to build tunnels in the environment, like a rock environment in this case, or soft ground, like with other tunneling methods. Then I would like to expand a little bit more on the QSystem, which is a core part of the Norwegian tunneling approach. And finally, I would like to talk about just basically mainly 2 examples, but one example is actually from 3 projects in Norway, very recent projects. And as a summary, in the end, I would like to talk about the differences between the Norwegian tunneling method and NATM, which is widely used also in India. Norwegian tunneling started, as with most of the tunneling methods, in the mining activities. And this goes back in Norway into the 18th century, even earlier, but let's say more planned in the 18th century. And from then on, it was developed further and further into other applications. And in the late 19th, early 20th century, the development of hydropower projects in Norway was experienced a big boost, and that also helped the development of the Norwegian approach of tunneling. And in line with this, the rock mass rating system, the so-called QSystem, has been started to be developed in the late 60s, early 70s, and the QSystem was then published the first time in 1974. So that's quite some time ago, and since then the QSystem has been updated on a regular basis based on additional experiences, additional case histories. Today, a very recent statistic is actually the next few lines down there, there is an impressive number of 750 railway tunnels, and I'm sure this statistics is actually a few years old by now. I'm sure there are more railway tunnels by today, and the same with road tunnels, southern road tunnels. My first interesting experience in Norway were the road tunnels when I drove up there, and I realized these tunnels are unlined as compared to other tunnels I was used to from the continent. So this is probably one of the main differences I will come back to later on. They have also a large history of subsea tunnels, and this is actually, they have 35 subsea tunnels by now, and a whole number of powerhouses for hydropower schemes and power tunnels. And they also have a history in oil storage and gas storage caverns, which are typically unlined, which is also quite well known. To a lesser extent, TBM tunnels are being built, and that one of the reasons for that is, of course, the hard rock, which is a bit of a bigger challenge for TBM tunnels than, say, a normal standard strength rock. Now, the civil tunneling amounts to about 7 million cubic meters of rock excavation every year. About that, in 2016, it was the...
Sorry to interrupt you in middle. Can you please able to share your screen? The presentation is not yet visible.
Oh, sorry for that. Thank you very much. Okay. You see my screen?
Yes.
Yes, now it is visible.
My apologies for that. For whatever reason, I hit the wrong button. So we have in civil tunneling about 7 million, or maybe meanwhile a bit more, of cubic meters of rock excavation per year. And mining, the rock excavation for mining is even more. It amounts to about 10 million cubic meters per year. So there is a substantial experience in underground construction in Norway. So that summarizes the history. I would like now to talk more about the fundamentals of the Norwegian tunneling approach. And I'm more talking about the current or modern approach to tunneling. It was, of course, a development over the past 60, 70 years, but I would like to focus on what is done today. One of the fundamentals is the ground investigation. A good ground investigation is really necessary for application of this tunneling method, and that's not very different from other tunneling methods, but I just wanted to, and I will come back to this here, I wanted to emphasize that because that's very often forgotten or not very highly rated, because people believe that we know enough about this rock, or about this ground, and we can actually build a tunnel without a lot of risk. Ground investigation or lack of ground investigation adds significantly to the risk of tunneling, and hence this is something where we can reduce risks for tunneling. Another fundamental approach in the Norwegian tunneling is that it is a method where it is adapted. The rock support is always adapted to the rock mass conditions, and that's very, very important to make this distinction between this rather modern technology than to old technologies which were used, say, 100, 150 years ago, where there was not so much understanding of rock pressure and rock conditions, and basically a support was put in there to fight the ground rather than to work with the ground. And that's a very important point in modern conventional tunneling. And it uses the rock mass strength as part of its support. That's also quite a fundamental importance. It's not like, as I said, fighting against the rock. It is taking the ground, taking the rock as part of its supporting system. I mentioned the QSystem is something which is a fundamental core piece of the Norwegian Tunnelling, where based on a rock mass classification, the selection of the ground support or the rock support is being made. And also, it's an observational method. The adaptation of the support to the rock mass condition during the construction forms an integral part of this method. So it's not like there is a pre-defined support and this is being applied throughout the tunnel or throughout a certain section of the tunnel. As always, the observational part of it, which is helping to improve the support if necessary. And the support, which is typically ground rock reinforcement by rock bolts, rock dowels, and shotcrete, that's considered for both, for the initial support as well as for the permanent support. And I will come back to this in a bit more detail. Very rarely they are using continuous secondary linings as part of the permanent support. It's typically not considered being part of the permanent support when you apply a concrete lining, for instance, which is very frequently used for civil structures like railway tunnels or road tunnels. Coming back to what I mentioned at the beginning, the ground investigation. The Norwegian Tunnelling Society has drafted up a general overview to include all the important pieces for the pre-construction and for the entire investigation, which includes pre-construction investigation, ground investigation, as well as the investigation during the construction and then during the operation, but primarily pre-construction and during construction are the main parts of the investigation. And when we start with the very early stages of a project conception, where there is basically a basic knowledge, a general knowledge acquired on the ground conditions. So this is the goal for that is to recognize the major challenges. First of all, like high overburden, or what is the cover above the tunnel, or are there major faults or even mantle faults or something like that, which are overthrusts, which may have an impact on the tunnel structure itself and its construction method. So these major parts are covered in the project conception, and that is followed by a feasibility study, which is more than focusing on aerial photographs and some spot field investigation, not necessarily entire alignment, but certain key locations which are determined based on the feasibility study and the study of aerial photographs. And then, of course, it's always good to have some visits if there are excavations done nearby, to visit those places to find out the experience which has been made there. And that is then carried into the detail investigation. So based on the feasibility, also the detailed investigation program is being defined, where there is really a detailed engineering geological mapping required, geophysical investigation, of course, drilling of boreholes and sampling for laboratory tests. Now this is the pre-construction. Based on this, a picture is being developed in the final design, which is then used to start the construction, during the construction, because during the design, we always make assumptions. So those assumptions must be verified during the construction. So that means that during the construction, tunnel mapping, a detailed tunnel mapping of the excavated or exposed rock faces is required. Then monitoring of deformation of rock stress features and so on, and sampling, and probably additional laboratory testing is being carried out during the construction. And then during the operation, of course, that's a different scenario where then during the operation, of course, further monitoring is being carried out, frequently monitoring instruments, certain monitoring instruments are kept left in place and kept monitored during the operation to find out the long-term performance of the tunnel support to make sure that the operation can be continued. Now, when we go back to the pre-construction ground investigation, I mentioned already what are the basic elements of this pre-construction ground investigation, and I'm very much emphasizing this is a very important part of the overall project, because you want to know what you are dealing with out there in the field when you build the tunnel. Of course, we know there's limited access to tunnel horizons if there's a very high cover or overburden above the tunnel. When we have hundreds of meters or even probably more than 1,000, 2,000 meters of cover above the tunnels, it's very costly and sometimes also difficult in terms of access to do deep borings, deep core borings, and sometimes these high overburdens prohibit the use of boreholes. So you have then to revert to what I referred to before, to some investigation during the excavation, which I will come back then afterwards. But what is also an interesting, relatively recent development is directional drilling, and directional drilling has been used primarily for installation of infrastructure like pipelines or a cable ducts or something like that. Now, directional drilling is nowadays also used to obtain cores of the ground, and you can almost go in any direction along the tunnel alignment or across the tunnel alignment, and to secure cores from that, to first of all investigate into the ground, inspect the cores, and also do then sampling for the laboratory tests which are following afterwards. So that's more and more becoming part of the detailed investigation these days, in particular in areas where access to tunnels is difficult or high overburden is prohibiting actually any real deep drilling. Of course, laboratory testing, what I'm just mentioning here is to check the mineralogy, test the strength of the rock in unconfined or triaxial tests, compressive stress tests, point load tests, which are very quick, very simple tests, but give you a good impression on the rock strength. And I'm saying point load tests can only be used on rock, on real harder rock or more brittle rock. It cannot be used on soft rock and or soil anyway. And then also, of course, the fault and shear zones are a very important influential parameter on tunnels, and you will have, I'm 100% sure you have the experience where fault and shear zones have a major impact on the tunnel construction, tunnel safety, and also, of course, on the cost, no doubt about that. And then rock stress measurement, as far as you can do that as in hole or in borehole, geophysics tests. You can sometimes measure that, and this all leads to the assessment of the quality of the rock mass along the tunnel lining or alignment. And when it then comes to the ground excavation, to the actual construction, we're switching to the observational approach, observational method. And I know that the term observational method is in some countries not very well taken, and it is probably because the observational method has been often misunderstood. I've been told by somebody many years ago, oh, you guys with the observational method, you're just looking at it, and if something goes wrong, you repair it. That's not observational method. The observational method is a very well planned, it's not an unplanned process, it's a very well planned process which allows you to respond to certain behavior, ground behavior or support behavior, so that you have a certain set of tools ready in case that the behavior of the ground or the performance of the support is not as expected. And I just wanted to make sure that this is not misunderstood again. Observational method is a very well planned method. It's not an unplanned where you basically go into a mountain and drive a tunnel in there, and then you look what happens, and if something goes wrong, you repair it. That's not the point, and that's not the goal of observational method. Now, when you excavate a tunnel, you install typically an initial support, which for the Norwegian approach is primarily rock reinforcement and shotcrete, as I said, reinforced shotcrete. And the rock reinforcement typically consists of rock dowels or rock bolts, and the shotcrete, spray concrete, it is also called, is typically reinforced by steel mesh, but increasingly by steel fibers or plastic, synthetic fibers, which is primarily in high deformation surroundings or high deformation environments used because the synthetic fibers have an advantage that they can sustain relatively high elongations without losing the without losing the tensile strength. And together with the initial support, the final support is being designed, but the final support is then typically checked against the observations during the construction. When the construction and post-construction period shows that the support which is installed requires additional support elements like additional rock bolts or additional shotcrete, so this will be installed before the handover, before the opening of the structure, and that's an interesting difference to probably other conventional tunnel construction methods. And I talked already about the initial and final support, what it consists of. Now, when you build a tunnel by the observational method, there are a few typical things you're applying. One is probing from within the tunnel. This is when you probe ahead of the face, and this is by now an almost integral part, in particular in soft ground tunneling, that you probe ahead of the tunnel face. But even in rock tunneling, in particular where there's a high overburden, where there is limited availability of pre-construction investigation data, and you're probably expecting a jointed zones, a sheared zone or a fault zone ahead of yourself, you drill holes ahead of yourself through the tunnel face to investigate the ground ahead of yourself. That can be just to make sure that the groundwater conditions are explored, or you can even go further by obtaining samples, testing samples for rock strengths and rock mass strengths, and so on and so forth. But in addition to that, sometimes it's required to also investigate the ground around the tunnel, and that's, for instance, in areas where you are expecting like karstic solution features, where you want to make sure that there's no major cavity next to the tunnel, which you might not see during the tunnel construction, but it could be next to the tunnel. So these probe drills and probings are used to investigate also the surrounding of the tunnel, not only ahead of the tunnel face. And then tunnel mapping. Tunnel mapping should be an integral part of basically every tunnel tunneling method. I understand in TBM tunneling there is limited opportunity to do some mapping, but there are other ways of assessing the ground conditions. But this is now a conventional tunneling method where you have the advantage of an open face, an exposed face after blasting or after excavation. So the assessment of the rock mass quality by assessing the joint settings, the groundwater inflow, and obviously, of course, also taking some rock samples, maybe for further testing, and also describing and assessing the mineral contents, which is very important for the durability sometimes. Just think of sulfates in the ground. Then all these data need to be collected during the tunnel mapping. Another element of the observational method is the tunnel monitoring. Tunnel monitoring is generally reduced to tunnel deformation, which is actually not the only part of monitoring. It's the tunnel deformation. It is it includes also visual inspection. How is the ground responding to the excavation right after the excavation, or probably a few months afterwards? So what's the development of the performance of the rock and the installed rock support around the tunnel? Because of course you have typically only access to the exposed face before shotcreting. If I would say in the majority of the cases, you're using shotcrete to cover the surface of the rock, and then you don't see there anymore. But then you have to observe the support for cracks, for instance, or for deformations, or when you have rock dowels or rock balls, you are inspecting the face plates, whether they are deformed, whether they are indicating that they are loaded or probably even overloaded. And all this picture is put together in a behavioral matrix, basically, where the tunnel, the entire monitoring of the tunnel, not only the deformation monitoring, but also the whole behavior of the tunnel and the performance of the support is being summarized, so that you can make an assessment whether the installed support is sufficient or it needs some further additional support or improvement of the support. And then, of course, in particular, in specific cases where there is question marks about the rock quality on the long term, rock quality can change and rock mass quality can change over time. So testing of collecting rock samples and testing of samples may also be part of the observational method. And it's not only about the strength, but it could also be chemical tests and slake tests and so on. I've experienced in one place the change of rock strength due to contact with water, which was surprising to the designer and the contractor, and that led to major instabilities of the tunnel, because it was during the construction, it was not obvious that this phenomenon would take place, and when this was a hydropower tunnel and when it was flooded with water, after a while the deterioration of the rock started, and the rock was basically overstressed and led to rock failure. Now, let me make a few comments on this typical approach which I described before. We have to differentiate between the rock and the rock mass. Very often these two things are put into one pot, if you will. There is a difference. The rock itself is the material. The rock mass is the entity of the rock, including all the features in there, like joints, like fractures, including the degree of weathering and stress conditions. So that's the rock mass. And the rock mass rating system tries to assess the quality of the rock mass, not the rock. I mentioned before that Norway is located in the hard rock province, so it has prevailingly hard rock conditions or rock conditions, and whether it's fractured or unfractured, but it's still rock. And the system of rock mass assessment, rock mass quality assessment in the Norwegian approach does not necessarily take into account what is the rock, the material itself, what's the condition of that. Yes, there are ways of assessing that and including that into the assessment, but it's not necessarily part of the direct input. And hence it is primarily developed around hard rock with a low chemical weathering. And yes, it can take into account fault zones, but as I said, only by adjusting certain parameters. So in this environment, the Norwegian tunneling has been developed and furthered, and it has come along a very long way, and is a very established and proven method today. And the goal of this method is to build tunnels with good stability, build them as fast and as cost efficiently as possible, and of course as safe as possible. And again, with a tailored support to the individual rock mass quality of the individual tunnels. Now you may ask yourself, what's the difference now between Norwegian tunneling and other conventional tunneling? And I'm talking about more modern conventional tunneling rather than what has been done 150 years ago. And that's a very good question. And there are two fundamental differences. One is the type of tunnel support. It's the support, how the support is considered. And I will come back to that. I've indicated it already before, but I will come back to that. And then the definition of the tunnel support via the rock mass rating system, as the QValue system. These two things are fundamental differences to other conventional tunneling systems. In the Norwegian tunneling approach, the initial and permanent tunnel support are kind of integrated. They are not two different layers of support, they are integrated. And they are primarily rock reinforcement, as I said, with rock dowels, rock bolts, may it now be spot bolting, or is it as a systematic bolting? Both is being applied. Spot bolting, obviously, in very good rock, systematic bolting where there is a fracturing and jointing system in the rock mass. And the shotcrete or sprayed concrete can be applied in certain locations or as a continuous shell, and maybe reinforced with mesh or fiber reinforcement. And I also mentioned the synthetic fibers are also frequently used these days. I have to say that fiber reinforcement is is taking over basically from steel mesh reinforcement because of its practicality, because of safety considerations, and also because of it's much faster to be applied. I mean, the staging is different. You don't need to put up the mesh and then spray the shotcrete. You can spray basically the reinforcement with the shotcrete, which is a much faster approach because you're cutting out at least 2 construction stages. In addition to that, in particular for the permanent support, the use of what's called the shotcrete, reinforced shotcrete arches or ribs is an additional permanent support, where at certain locations in certain distances the initial support is enhanced by the installation of reinforced arches, shotcrete arches of a certain thickness with a certain steel mesh and so on. And when we come back to the use of the QSystem, you will see certain recommendations which are made there. So these ribs are a replacement to the continuous shotcrete or concrete support linings, which is used in other conventional methods for the funnel support. And if there is a cast-in-place concrete lining, for instance, or a shotcrete lining, then it's typically not considered being a part of the permanent support. Only in very poor rock conditions this is considered, but as a standard approach, it's not considered. Excuse me. I mentioned already the QSystem, the rock mass classification system, also called QSystem, is a core piece of the Norwegian Tunnelling, and it is based on precedent experiences, they are all collected in databases gained from numerous previous completed projects, and this database is updated on a regular basis in order to further inform the QSystem and support charts. And the support requirements are assessed based on the Q value. And the Q value is then also combined with sizes and safety requirements for the tunnel to assess the amount of support. And we will come back to that a bit later. Now, the Q value is assessed as a function of basically 6 parameters, which are, first of all, the RQD, which is the degree of jointing, and the joint set numbers, which means how many different joint sets are met, the condition of the joint, whether it's rough or smooth, or the joint roughness number, the joint alteration number, which is referring to any coating, any infilling in the joints, then the joint water reduction factor, which we all know that the presence of water reduces the shear strength along shear planes, and the stress reduction factor, which is again, and I will come back to that later, a function of the tunnel size and other input parameters. The RQD, when we combine those 6 parameters, which we just here showed, when we combine those, they are describing the stability of the opening. The RQD over the joint number gives you the degree of jointing. The reduction factor and the alteration factor gives you the joint friction, and the JW and the SRF gives you the active stress, which is acting upon the tunnel circumference. Now the RQD is determined in two ways. If you typically in the pre-construction phase where you have core logs or you have cores which you're logging, so the RQD is the sum of the length between the natural joints of core pieces which are more than 10 centimeters or 2 times the core diameter. So what it means is it's the sum of all intact pieces between natural joints over the entire length of the total core length. So it's a percentage. When you are inside the tunnel, when you excavate, and as I said, as I alluded before on the observational method, you don't have a core. You can potentially assess the RQD along a line at the tunnel face, or you assess the RQD per cubic meter, and that's a formula by Palmström, where you are using a joint number, the number of joints per cubic meters, to assess the RQD. And when you put these parameters together, and I will come back to the parameters later on, you are ending up in a chart. And this is the chart which is published by the Norwegian Geotechnical Institute, which gives you an impression of the various different rock mass qualities and the support required for those rock mass qualities. This is just an additional sheet for using the or for explaining the rock support chart, and this updated sheet also provides you now with the addition of reinforced shotcrete ribs, and also provides you with the additional information on the energy absorption requirements if you use steel fiber reinforced shotcrete. And I'm not going into all the details here because this would be a day's training to go through the QSystem and assessing support requirements based on the QSystem. And I say that purposely because it's very often misunderstood that the QSystem is a very simple way of assessing the support. You just eye in a value and say this is required. You need 15 centimeters of shotcrete and 4 meter long rock bolts on a pattern of 1.5 meters by 1.5 meters. It is actually required to thoroughly assess the ground conditions and thoroughly assess those parameters. And this chart, which I'm showing here, is primarily applicable to the tunnel roof, the tunnel shoulder, and the upper sidewall areas. When you want to use this for the design of the sidewalls alone, you need to use certain conversions of the Q value in order to reflect the tunnel height, the height of the wall. So instead of the tunnel span, you use the height of the wall as part of the input parameter. The handbook for using of the QSystem gives some suggested values for RQDs in certain conditions. And you can see here, very poor would be more than 27 joints per cubic meter, and you put a certain RQD in there from 0 to 25. You see it's a very wide range, which is, of course, having a major impact on the result at the end. And it also gives reference values for the joint set numbers when you describe the ground. So like a massive no or only few joints, you give a JN of 0.5 to 1.0. Again, major differences which make major differences in the result, in the final result, if you don't really properly assess and scrutinize those numbers. The same applies to the joint roughness numbers. As we said before, the joint roughness very much influences the joint behavior, the shear resistance along the joints, and that's a very important parameter, of course, dictating also the stresses acting upon the tunnel. And you can go through all these different categories, from discontinuous joints to slick and sided planar joints and so on, and you can find out the GR. And another governing factor for the stresses acting upon the tunnel is how the joints, whether they have coatings, mineral fillings or sand fillings or things like that. So all these values can be taken from those tables and can be used to be put into the QValue equation. And again, and we will hear that more often from me today, again, this is not just plugging a number because it could be all right, could be like that. Let's put that number because depends on the number, what number you pick, it may have a major impact on the final result of the Q value and hence the final result of selecting the support. And the joint water reduction factor, we know that when there is water inflow through the joints, and in rock the water inflow is primarily along discontinuities, along joints into the cavity, you have an influence of that water on the shear strength along the joints, and that has an impact on the pressure, on the support pressure or the load acting upon the tunnel circumference. The stress reduction factor is a function of the ground condition and the size of the tunnel. And you can see here there is various different ground conditions given in this table, from only weak zones to competent or mainly massive rock or squeezing rock and so on. So you have all those differentiations in the SRF value, which you use then in the equation. But in addition to that, it also requires to take care of the safety requirements. And the safety requirements are reflected in the excavation support ratio, which is assessed based on the span or the height of the tunnel. And of course, also it's influenced by the different safety requirements for different function of the tunnels. So there's a different safety requirement, say for a hydropower tunnel, where you have a bypass tunnel where there is no pressure, no pressurized water in there. It's just a normal free flow tunnel, and you don't really mind if there's here or there some rock smaller rock pieces falling down. Whereas when you use the same approach in a railway tunnel or in a road tunnel, it's a major difference, of course, because you can't afford that a rock piece falls off, and even if it's a small rock piece, it's falling off the roof in a road tunnel. And of course, in different countries, you have different safety levels, safety requirements, I would say. When you can assess due to the various different types of excavation you see in this table here on the left side, the types of excavation, and you can assess certain ESR values, but there are also recommendations where the combination between ESR and Q value plays a role, where you have like when you have a Q value of smaller than 0.1, there's a high potential of stability problems, and hence you need to upgrade the ESR value. And this leads, and you will have seen this, if I may switch back to this chart. On the left side here, you have span or height, depends on what you want to assess, roof or side walls, over the ESR. And you might have asked yourself, what is that? That's the equivalent tunnel dimension, which is assessed by span or height over the ESR. So you see, it's not a simple system, but just plugging in a few parameters and you're done with your assessment. It's a relatively complex, integrate and interacting system. Here are suggested or recommended values for the ESR, again taken from the 2017 handbook of using the Q system. Now, a few notes for the use of the Q system, and I have already started indicating these things. It has been developed for hard rock materials primarily. It has been adjusted to less strong rock materials, and certain parameters or certain corrections of parameters have been introduced. But when you look at the chart, and if I may switch back again to the chart, you see here 9 and 8, where you basically have exceptionally poor or extremely poor ground conditions. There is one criticism from my side. It's not a criticism, but one comment, one note to be taken into account. The efficiency of rock bolts or any rock reinforcement in such a material with a relatively low shear resistance or shear strength is reduced. In other words, the softer the material, this rock material, the less efficient the rock reinforcement becomes. And this is something which needs to be taken into account at a certain stage. And I would assign this to this left top corner area, or left area of this chart. At a certain stage, rock reinforcement doesn't provide you any proper support anymore, and you have to rely on a shotcrete lining as an initial support, and potentially on a secondary support by a cast in place concrete or continuous shotcrete lining. I'm just making you aware of this because unfortunately, I've seen examples where in very, very low shear strength material, rock reinforcement has been used because they derived it from this chart without considering that the rock reinforcement doesn't really do any, and doesn't have really any effect anymore. And there is a clear limitation stated in this handbook where it says the majority of the case histories, which is the basis for the QSystem are derived from mainly hard jointed rocks, including weakness zones. So there are weakness zones, but primarily hardened rocks with joints. From soft rock with few or no joints, there are only few examples. And by evaluation of support in such types of rocks, other methods should be considered to be used in addition to the QSystem for the support design. It is important to combine application of the QSystem with deformation measurement and numerical simulations in squeezing or very weak rock. And I think this is a fundamental statement which is very often ignored, unfortunately, in practice, because it seems to be so handy to use this chart and to come up with a support and be done. It needs a very thorough review of all this data. Another set of notes is the pre-support or forepoling is not part of the support chart. It's not mentioned in the support chart. It's not. There's no such pre-support offered in the chart as part of the support. The handbook itself refers to poor rock mass quality of less than 0.1 to 0.6, depending on a tunnel span where you should use pre-support. You can see already here it's quite a wide range of Q values between 0.1 and 0.6, and even depending on tunnel span, you make the decision whether you want to use pre-support ahead of your tunnel phase or not. And this tells you you need to have the experience to use this system. It's not like somebody who has no experience in tunneling can immediately design a tunnel support. It provides very good results in sound and fractured rocks and hard rock, and this is proven, and this has been shown in many projects. There have been failures as well, but I'm always careful of saying this is a failure of the system. It's most of the cases a failure of those who implemented the system. What it also needs, it requires close inspection of the rock surface around the entire tunnel periphery before you apply the shotcrete. It may require hammer tapping or scaling, so you can check whether there are any loose rock slabs or rock blocks. When you look for small cracks which may have an impact, you have to have a closer look, and I will come back on all those arguments with additional comments. I'm sorry, was there a comment? Okay. And also altered rock, also basically chemically changed rock, may look very similar to good rock, to hard rock. I've experienced it myself, and I found my problems with it. I'm sorry, is there any comment?
May I request to the participant kindly mute yourself?
So it may look original, fresh, like weathered, fresh rock, but when you look from it at a distance, but you need to have a closer look. And the support chart does not immediately suggest support for squeezing ground or soft and weathered altered rock. You need to go into assessing the parameters in order to assess the support requirements. Now here are a few comments to that. When you look at the requires a close inspection here, which is very true, but there are safety requirements in the tunnel. Frequently or typically you cannot access the tunnel face after blasting directly for various different reasons. One is the safety. There may be falling rocks, there may be instabilities in the face, but also there is a tunnel excavation equipment around and conveying equipment around, which also poses some safety risks to the geologist who is out there. Then it takes time. You need proper lighting, proper illumination for good visibility, and there is very often dust and these things around. And I've done phase mapping for quite a few years in my career, and I know exactly how difficult it is for the geologist to stand at the face, take a proper phase mapping, and behind you there is already the crew waiting to muck out the material which has been blasted, because they are paid by the cubic meter, they are paid by the production, they want to carry on, they want to achieve meters and tunnel progress. So it's very difficult to find the right balance there, and there is of course a high likelihood that you are missing features and you're missing certain input parameters, or misinterpreting certain conditions for input parameters. That's just to keep in mind. Hammer tapping, same thing. Often you have a 10 meters, 12 meters high tunnel. How do you get there? You need to get some lifting device. Lifting devices, proper lifting devices, are typically not near the face. They are somewhere behind. So you have to get some lifting basket, and you won't get any tunnel foreman to get the lifting basket forward because it's in the way of the other equipment, and you are not allowed. You should not climb onto an excavator bucket to get up access to the tunnel roof. So these are all very nice requirements, but in practice there is always some compromise to be made. Same applies for when you want to see small cracks and so on. So you must have an experienced geologist who is familiar with the type of rock and familiar with the type of features which can occur in this rock or rock mass. That's very important too. It's not, you have to have somebody who sees these things. When it comes to squeezing ground based on your observation of the deformations and so on, you need to change the approach to assess the support, and you need to use the recommended adjustment factors of SRF, for instance. Now, just as a summary to this rock mass classification and determination of tunnel support items, as I said already, it provides good results in sound to fractured hard rock, where the rock material itself is good quality. It does provide limited applicability to soft rock, soft ground tunneling, and that's where other conventional methods may be better suited. In the handbook, it says the support chart gives an average of the empirical data from examined cases. In some cases, the rock support represents a conservative magnitude of support, while in other cases, cave-in occurred during construction or years later when the underground excavations were in service. Now, the latter part of this sentence, you don't want to get, you don't want to get there. You don't want to, wrong button. You don't want to experience any cave-ins, neither during the construction nor during the following years in service. So you need to be very, very careful in assessing your support, and you need to have good experience in assessing the input parameters which are used to assess the Q value and the equivalent dimensions, and then the support. And I keep emphasizing that because I have seen, unfortunately, a lot of abuse of that system, and then afterwards it was always claimed, oh, the QSystem doesn't work, or the Norwegian tunneling method doesn't work. I have used both. I've used the Norwegian tunneling method as well as the NATM. Logically, and probably you have realized from my accent, I'm coming from Austria, and I've used NATM a lot in rock primarily, but also in soft ground. But any system needs to be implemented by experienced engineers and geotechnical engineers. And there's also one other requirement I have. Please use the handbook, the full handbook, which is provided free online by the Norwegian Geotechnical Institute, because it gives you very important insight, and it's not like you pick out just a chart or a few pieces and you're done. Really use that handbook for your assessment. This takes me to the examples, which is the almost final part, where I'm just describing actually in total it's 4 projects, but I combined one project. It's a Norwegian, these are 3 Norwegian projects which are currently ongoing, and another project where I can't really say where it is from because there's a court case ongoing on that, but there were certain things going wrong, and there was also one of the underlying questions during the investigation. It was the Norwegian tunneling method the right tunneling method, or should we have used a different one? And I keep that question open actually, because I think it has its reasons why things go wrong, and typically it's not necessarily only the system. Now this is, as I said, these are railway projects in Norway, so basically the home country of the tunneling method, and it's a typical profile of a 2-track railway tunnel. They're in this case relatively good rock. This is the support class number 1, which includes systematic rock bolting, and it includes systematic application of shotcrete. They're using steel fiber reinforced shotcrete there, which is I think it's 80 millimeters thick, so it's not very thick. It's a thin layer of shotcrete, and they are rock bolts, and they are using 2 different types of rock bolts. Some are mechanically anchored, some are fully grouted rock bolts, and they are on a pattern of 2.5 by 2.5 meters with a length of 4 meters. So you see it's an almost 14 meters wide tunnel, and they're using 4 meter long rock bolts. These constructions are underway, and quite significant lengths of tunnel have been constructed in various different ground, and so far it was a success. This is now what they call a support class 2, which you can see the difference to support class 1 is a higher density of rock bolts, same type of rock bolts, and but the shotcrete itself, the shotcrete thickness itself is unchanged. So you can see how much the system, the Norwegian tunneling system, relies on the reinforcement of the rock around the tunnel opening, and basically using the rock itself as part of the support. As I said, this is not much different, for instance, than from NATM. Just wanted to mention here, you can see a secondary lining in here. And as per the design, the secondary lining is not used as part of the permanent support. The permanent support is what you see here, is the rock reinforcement and the shotcrete. The secondary lining is there for water protection and for protecting the waterproofing membrane. There's a waterproofing membrane. This is the thread dashed line between the shotcrete primary or initial or main support, sorry, and the concrete lining. So the concrete lining is not used as integral part of the support. This is the support class number 3. Again, we are talking about a Q value of 1 to 4 here. Sorry, I forgot to mention the Q values before. When you go into the best class, they have a Q value between 10 and 100, quite a wide range. And then here for the support class number 2, the Q value ranges between 4 and 10. And then number 3, and we're getting into the lower numbers between 1 and 4 Q value. And you see it's a denser, much denser pattern of rock bolting, rock doweling. And you have a thicker lining of shotcrete. It's 100 millimeters thick, and you have also a different strength. So you're increasing the tunnel shotcrete, and as I said, the concrete lining is not taken into account. It doesn't change. In the support class number 4, which refers to Q values between 0.2 and 1, they increase this designer increased the systematic rock bolting density, and also increase the thickness of the shotcrete lining to 150 millimeters. So these are typically support cross sections or support systems which are used at the moment in rocky material. So now they have also to deal with with various zones of faults with very low Q values, where they are splitting up the face into a top heading and a bench excavation. All the previous excavation was done in full face excavation. So the blasting is all blasting excavation is done in one single excavation step, whereas in this even less stable ground or stable rock conditions, they are splitting it up into a top heading, which is the upper part, and in the bench, the lower part of the tunnel, in 2 different separated steps. Also, there is pre-support used. I was talking about the 4-poling before, or pre-support, and they use here in this case rebar 4-poling, which is grouted in place, and they use shotcrete, 200 millimeter shotcrete thickness, and a thickness of and an additional a higher density of the rock bolting pattern. And then there comes an even, it's basically soft ground, or there's still rock material, but a soft ground where there is not only the stability of the upper part of the tunnel to be taken into account, but also due to groundwater conditions and the lack of strength of the material, there is significant load onto the tunnel invert, which means that the tunnel invert had to be curved or dished, and there is a thicker permanent tunnel invert concrete. And I was referring to the reinforced shotcrete ribs, and in this part of this for these projects, one of these, just take out one typical rib here, which they are using, which is basically at a rock bolt location. You have additional reinforcement. In this case, it's mesh reinforcement, but sometimes you can use lattice girders or steel bars fixed in place, and that is a local thickened shotcrete part, which is between which is on a certain distance here. In this case, it's 2.5 to 3 meters, and that's part of the permanent support to enhance the initially installed support. So this is Norway today. And this is the project which I was briefly indicating before. It's a hydropower scheme, and you see a typically or mostly unsupported tunnel cross section here, where you on the right side see there is basically no shotcrete, no support, because the rock conditions are sufficient. The jointing of the rocks is favorable, so that there is no fallouts to be expected. However, in the roof and the left shoulder, they needed to implement rock support by shotcrete, and you can see the rock dowel heads here sticking out. So this is typically one of the best rock classes which was available in this project. This is a cross section showing full support of shotcrete from wall to wall with a systematic rock doweling, also fully grouted rock dowels, not mechanically anchored, but fully grouted rock dowels. And this is how the tunnel looks like. It's about 6 meters by 5.5 meters or 5 meters, dependent on the shape. And you can see actually here there was some over excavation during the construction for reasons which is beyond this scope here. But that would have been the theoretical excavation shape. This is another example for a section where there is systematic rock bolting used in combination with the rock shotcrete. And the reason why I show this picture here is because we have water in these tunnels. And I said before, water plays an important role in the shear strength development along the joints in the rock material. And this was one of the reasons why there was a problem in these tunnels. Here's an example for, this is after repair. This is not, of course, before the repair. This is an example of what can happen. You see, this was the tunnel originally built, and there was a major fallout along steep shear planes. And these steep shear planes were partially the reason for the fallout. The main reason was that the support which has been implemented in the first place was not sufficient to stabilize over time the area close to the tunnel. So it started unraveling, it started opening up, and that then destabilized this major material here and blocked the tunnel. The problem was that these water tunnels have been blocked. That's another example for a major fallout along the steep shear planes. So what I want to show here is that very often this has not been seen during the excavation, during the construction. These shear planes, if they would have been identified, I'm sure that the designer there at the face or at the construction site and the contractor would have made the necessary changes to the support to make sure that something like that doesn't happen. And you see actually here is the original sidewall of the tunnel, and on this side, and this is the over excavation, or the fallout. Sorry, it's not over excavation, the fallout, which happened after time. This happened actually after the tunnel was in place for a year already, and it has been then flooded to run the turbines, of course, and that it wasn't an immediate fallout. It was a fallout which happened probably 2 years after excavation. That's another example for a major fallout. What happened here is, you see in the background the original tunnel, and there are shear planes, more shallow inclined or almost horizontal shear planes. What happened there was that the shear plane, as long as it was visible in the tunnel support was accordingly, it was selected accordingly. So the tunnel, you can tell the tunnel is still in place here. And as soon as the shear plane left the tunnel roof, was going below, the shear plane was coming up from the inward of the tunnel and moving across along the tunnel alignment, moving across into the tunnel roof. And as soon as it disappeared in the tunnel roof, the geologist who was doing the mapping there, who was not experienced enough, did believe they can change the tunnel support and reduce the tunnel support. This collapse did not occur right away. It occurred as soon as the tunnel was flooded. So there was an internal contact with water. Again, the water plays a major role. Before, the tunnel was open and it was basically drained. And suddenly, when the tunnel was flooded, the groundwater in the groundwater content and of course the head as well in the surrounding rock increased, and the shear plane, which was accompanied by soft material, failed and the tunnel collapsed. This is another collapse.
Hello.
Sorry.
Yeah. Can I take a minute, please? Sorry for the intervention. Now I would now look towards the winding up, because we want to leave some time. I'm sure there are a lot of people now who have a lot of questions to ask you. So at the end, we should have some time for answers. So request you to now, wind up, please.
Give me 3 minutes, please. Okay.
Yeah, thank you.
So we have this is another collapse area, major collapse area. You can judge based on the size of the height of the people. It was 6 meters above the actual tunnel. Again, a misunderstanding of the local geology. And here, this is a typically high stress feature in the tunnel roof, which has showed up only after a long period of time. And this is something which I referred to before, when certain rock formations tend to change their strength when it gets in contact with water. So in this case, this was a basalt which significantly reduced its strength when it got in contact with groundwater, and combined with the in situ stresses, it failed. It looks like a rock burst, but it wasn't really rock burst. It's basically a failure. And this is one of the repaired sections, but that's probably not so interesting. Now, the difference between...
Hello?
Yes.
Hello?
Yes.
Yeah, sure. You're very much audible.
Actually, as the Murphy's Law calls it, sir, today there's no light at our end.
I'm sorry, is anybody talking to me here?
Okay, gentlemen, please switch off. Please go on mute. The audience.
Right, so please bear with us, sir. Another 2-3 minutes. I have sent a message to Potty, sir, for the permission to begin.
Yeah, sure.
Audience.
All right, I think we can stop this here. I'm open for questions. Thank you.
No, just hold on. Control, can you put people on mute?
IT, please request you to keep all the attendees on mute.
Yeah. Okay. Please continue.
Okay. Very briefly, at the end, you have realized that there are not huge differences between the NATM, which you are probably more used to using, than the Norwegian tunneling method. Both require full understanding of the ground conditions, and both are using the ground as part of the support. But the difference is where the Norwegian tunneling method is more related to hard rock, to good rock conditions. The new Austrian tunneling method is also covering the soft rock and soft ground conditions. The Norwegian tunneling approach uses a rock mass rating system, while the new Austrian tunneling system is uses more a detailed assessment of the rock conditions and stress situation without, well, certainly based on certain experience, but more an analytical approach. And also in Norway, the secondary line, the concrete lining, is not so much used as part of the permanent support, whereas typically the Austrian tunneling method uses a concrete lining as a secondary permanent support. With exceptions, of course, sometimes it's not necessary even in a newer tunneling method. So that takes me to the end. A short selection of literature, you can read that yourself. Thank you very much for your attention.
Thank you, Dr. Zeidler, for finishing bang on time. Now the house is open. I'm sure our viewers, our attendees have a lot of questions to ask you. So ladies and gentlemen, should you have any questions, should you have any clarifications to seek, please, you can address your question. Just give out your name, organization, and give out your question to the speaker. Okay, till the others are warming up, I have one question. Yeah. Hello. Yeah, I have one question. You mentioned about the depth of the bore, depth of the boards. So how much is normally that, you said short or the deep, this thing, how much is generally the depth of the this thing taken hole?
I'm sorry, I didn't fully understand the question. Apologies.
In one this thing you mentioned that the depth of the hole, okay, it can be short also, or it can be very deep hole. Normally speaking, how much is generally the depth of the hole? Of which hole? Are you able to hear me? My voice is cracking.
Of which hole? Sorry, the depth of which hole?
I think there is some. Okay, the next question can carry on. I think till my voice gets restored. Okay.
Hello.
Okay, you can ask questions from others. I think there is some voice crack in my this thing. You can invite questions.
Hello.
Yes. Please.
Ankit Mishra this side from PMG Ranipur. I have a question regarding this thing. Like if I have encountered a bulging in my lagging work, like there's pore water being accumulated and the same has to be rectified. So is there any possible solution to drain out the same and to uninstall the lagging and to reinstall it using shotcrete?
So I understand that you have a cavity or a tunnel with steel lagging.
Yeah.
Is that correct?
In the
portal, you experience some deformation, some bulging. Is that correct?
Yeah. The portion where I'm using lagging in the initial 10 meters of the tunnel, there is bulging taking place. So if I want to rectify the same, so the lagging is to be removed. If we are removing a 2 or 3 laggings from the same stretch, so whether that is whole stretch of 5 meter to 10 meter will be under so much stress that it will it won't be able to, it won't be stable.
Yeah.
So how to rectify the same? The small portion of that.
Of course, that's very much dependent on what is the reason for this bulging. I mean, you are right. Groundwater may be one of the reasons, because groundwater may have reduced the shear strength of the material you're supporting there, or I would not expect that the groundwater the hydrostatic pressure will act directly onto your support, because you said it's steel lagging, and it's a permeable support. I guess the water could go through. Yeah. So I would say the groundwater is primarily reducing the shear strength of the material, of the surrounding material. So you could improve that by draining, by installing drainage holes into the ground, but I'm not exactly sure whether this is sufficient. And as I said, I don't know enough about your specific case, but you might have to install additional rock, or it is in rock, I guess. It's a rock material, is it?
It's a rock material, yeah.
It's a rock material. So you might have to install additional rock bolts. Do you have to do some excavation afterwards because the bulging went too far in, so you have to reprofile? Or what do you have to do there?
So do we have to remove the laggings first, or directly we can puncture the laggings using drainage holes?
You can puncture the laggings using drainage holes, yes.
Okay, thank you so much.
But you might have also to install some additional ground support there by dowels or bolts, because the drainage may not be sufficient. Okay. I don't know enough about your specific case to say drainage alone would be enough, but drainage frequently helps a lot.
Okay, thank you so much.
Hello, Mr. Kurt. This is Brijesh from NHIDCL. Thank you for this wonderful presentation. Now, I would like to ask one simple question. Are you aware of the uncertainties that are encountered in Himalayan geology, right?
Yep.
So the simple question to you is, which is the most versatile method? Is it NATEM or Norwegian tunneling method, owing to the uncertainties that we encounter in Himalayan geology? Most suitable method, is it NATEM or Norwegian tunneling method?
I would feel more comfortable with NATEM.
Okay.
I'm not saying that the Norwegian tunneling method is not applicable. I'm not saying that, but knowing that you encounter a lot of, or frequently, soft rock conditions and highly fractured and highly altered material in Himalayan zones, I personally would think that the NATEM provides you with more flexibility.
Yes. Okay. Thank you, Mr. Kurt.
I think if you would ask somebody who is one of the proponents of the Norwegian method, he would probably disagree with me here. But I mean, my experience, and I have experience in both, granted more experience in NATM than in the Norwegian tunneling method, but I have realized that in troublesome variable ground with potentially soft rock conditions, the Norwegian tunneling method reaches its limits.
Okay. Thank you.
Okay. Yeah. Hello.
Well, sir,
I've
got a question.
I was asking you that question. That was that, you mentioned that as you go along the excavation of the tunnel,
yeah,
you can make the investigation holes to find out as to what is the kind of a strata which is lying ahead. So normally speaking, how much is the maximum depth that you can achieve of the investigation hole?
Typically what you try to investigate is the next 10, 20 meters ahead of your fence.
Okay.
Yeah. Of course, again, this is very much dependent on the ground conditions and so on, but that's a typical length. Today, when they are using directional drilling, and you can do directional drilling even from within the tunnel, you can actually go further distances. It always depends on what you want to achieve with it. Frequently, you want to know what's the next few rounds of excavation blasts ahead of yourself, so you don't hit highly water containing material and so on. But 10 to 20 meters is a pretty standard length.
Your procedure. Thank you.
In rock.
Good afternoon, sir.
I'm sorry, just one quick one. I apologize. Just one quick one. That's in rock. In soft ground, you have shorter lengths. You take shorter lengths. Sorry, I'm back.
Yeah, good afternoon, sir. Can you hear me?
Yeah, good afternoon. I can hear you.
Yeah, I'm Colonel Deepak Patil. I'm the general manager for Silkyara Tunnel. I'm working here tunnel in a complete phyllite zone. These are all broken, poorly weathered phyllite rocks. And I have a question for you. What are the conditions when we can use the yielding elements? Under what squeezing conditions, and how do we come to know that this is the time to use yielding elements?
That's very difficult to say ahead of time without any monitoring in the field. But yielding elements are typically used where you have deformations in the excess of 100 millimeters and more, where it very much depends on your support. For instance, I have seen 100 millimeters of deformation or even more than that. We did not use yielding elements. At that time, we didn't have the yielding elements. What we did, we left slots open in the shotcrete lining, which were then closed by the deformation, and over time the deformation reduces. That's the difference between squeezing and swelling. And over time the deformation rate reduces, and at some stage you're closing those gaps, and then it stops, and the support can take over the support pressure. The yielding elements are used where you have larger yields, I think in excess of 100 millimeters, and they provide you with the advantage that they are not losing the support pressure. They basically deform while keeping the strength, and that's the big advantage. So I think I don't know exactly in your area, but you're talking about phyllite, and that reminds me of one of my tunnels, which was not under high overburden. There was not a lot of cover above the tunnels, but these tunnels deformed unbelievably, and we didn't have yielding elements back then. The yielding elements were in the experimental stage at that stage. So what we had to do, basically, we had to allow for these deformation slots, and then put additional support once the deformation started reducing or was leveling out. We added additional support to make sure that we're not overstressing the additional support. Yeah, it's I would say 100 millimeters deformation is certainly, but it again depends on what support you build in. If you build a very stiff support in the first place, that cannot cope with 100 millimeters, and you destroy it, because with the overstressing, it yields and it loses its support pressure. When you, in the first place, and that's what we used, for instance, when using the NATM, we allow for relatively flexible support, which is not be damaged or destroyed by flexibility, and steel fibers or even more synthetic fibers are helping with this, because even after the shotcrete cracks, there's still a residual strength in this shotcrete. When you use fibers or synthetic fibers, even more, you allow more deformation, and there is a definition of all this. You can define it in the specification. But when you are flexible in the first place, you don't need yielding elements right away. But you can accommodate depending on tunnel size, of course. But let's assume it's a 12-meter diameter tunnel, typically road tunnel size or railway tunnel size. 100 millimeters of deformation is nothing difficult for a shotcrete lining to take without losing its strength. But beyond that, and when you have concentrated in certain areas deformation, beyond that, then it will become difficult and it breaks, and you need to use the yielding elements.
All right, so the answer is taken, sir. But since we're still going into the tunnel, and right now the overburden which we have right now is roughly about 450 meters. What overburden you think should be creating a squeezing condition, and that is the time when I start using these yielding elements. Like you said, 100 mm of deformations and beyond. In my case, we have a slightly larger diameter tunnel, going to about 14 meters in diameter, and the squeezing conditions, I'm not able to yet understand that. When are the squeezing conditions going to start? Is it something beyond 600 meters of overburden, or maybe before that? Is there any thumb rule on this particular issue that in phyllites, after a particular overburden, that is the time when the squeezing forces start, the squeezing conditions start, and then you start using yielding elements? I've already fabricated some yielding elements, but I'm waiting for those conditions to come in.
Yeah. But of course, you need to know how much yielding you have to allow, how much deformation you can allow, and that needs to be analyzed based on the in situ stress situation versus the strength of the material. And when you talk about a phyllite, the phyllite has certainly the lowest strength along its not layering the I don't know what you call it, the phylitic layers basically. Yeah, the bedding planes basically. So you have the lowest shear resistance there, and when you compare the in situ stress against that, then you know then you can see when it is exceeded, the shear strength is exceeded, and when major deformation starts setting on. But that's really a question of an analysis you have to run.
So we'll have to basically do trial and errors and keep waiting for different results. And of course, we'll have to do a little over excavation so that we allow the primary lining to squeeze that much so that you get a correct profile finally.
Yeah. That's certainly a very good point. The over profiling, over excavation, because you don't want to go back afterwards after the deformation has taken place and you start excavating again and reprofiling again. That's very good assumption, but I would yes, trial and error is, in the end we always have to try it out, but I would suggest you have some basic fundamental parameters which you can use for a basic analysis, telling you what is the in situ stress versus the shear strength of the material, in particular, as I said, along the bedding planes, and then you can say, okay, here we have at 200 meters, or it could be even less. It depends really on the quality of the material, but I told you about this project which I was involved in. We had 60 meters of overburden and major deformation. It could be, in your case, it could be 100 meters, it could be even more, it could be less. You really need to look into the rock quality and into the parameters of the rock.
Right, sir. Right. So, what are the indications for squeezing conditions? What are the indications? I mean, how do you come to know that the squeezing conditions have started in phyllites, primarily in phyllites? The ongoing deformation. You always have a certain amount of deformation after the excavation, because the ground relaxes. You have to divert the stresses which were in the ground before. You have to divert them around the tunnel, and that involves deformation. But this deformation, if there's an equilibrium between the driving forces and the restraining forces,
is achieved, those deformations stop or at least level off and then stop, right? After typically a couple of diameters behind the tunnel face. When those deformations don't stop, then you have squeezing conditions.
Right, sir. Thank you so much, sir.
You're welcome.
Okay, and any other pressing question anybody has?
Good afternoon, sir. This is Farooq Khan here. Can you able to hear?
Yeah. Yeah, Farooq, you can open your video also so that we can see you. Yeah.
Am I audible?
Yes. Yeah, you can start your video also if you have.
Okay. Actually, sir, my question is, to Dr. Zeidler is this: what are the factors? As they said, it is an observational method. Norwegian tunneling method is an observational method. So after that observational method, we do take the blasting and all. We decide the support system based on the rock quality. Is it that's the thing? So my question in this is, what are the factors do we consider when for the seismic zones? Because we are considering only rock mass quality here. So is there having any design parameters for this seismic zones where earthquakes are generally occurred very frequently? Like fault displacements may occur, like slope instability and liquefaction may occur. So what are the parameters do we have to consider during designing stage? So
you will not find easily an answer in the QValue and the support system based on the QValue or any rock mass rating system. This is certainly a requirement where you have to assess the forces based on the seismic activity, and you have to apply this as additional load onto the tunnel support. So it's not, there is no ready factor, if you will, which you can take and say I have a seismic zone of X and that gives me a factor of Y, which I plug into the support chart. You need to do a thorough assessment of the loads acting upon the tunnel support before, in order to include the seismic loads. And the seismic loads are dependent on the seismic, are defined by the seismic zone and the energy in the acceleration rather per seismic event which is expected, which you're designing for. But that's an additional load. It's not like you can go into a chart and assess a factor and put that on top of your support. It needs a detailed analysis.
So much. It will require a detailed analysis of loads and other calculations, including the factors of seismic and other seasonal factors also.
Sorry, I did not fully understand, I believe.
Okay, Dr. Zeidler, I think now I can see as that time clock is ticking and a lot of our friends on the viewers audience have also started leaving. Maybe there are other engagements that everybody has. So we will try and close it here.
Thank you.
If you have the email ID. Ladies and gentlemen, should you have any specific question, please let us know. We will ensure that your question is fed to the speaker and we get a rightful answer. I'm sure Dr. Zeidler will like to answer that. In the meantime, let me thank Dr. Zeidler for a very elaborate expose on the subject of Norwegian tunneling method. One essential difference that he has brought out is that and it is more than 100 years old. When this methodology was started, it was primarily hard rock. Somebody raised a question, out of the two, which is more suitable in case of Himalayas? Well, I think he's already answered that when you have the conditions which are more a mix of soil and rock, then NATM is a preferable method than over the Norwegian method. However, decision has to be taken based on certain other parameters. But he's very elaborate. He's gone into a lot of details to elaborate the QSystem classification, and also how, based upon that classification system, how do you design the support system? That was the basic form of the entire thing. That how do you choose the support system based upon the Q system of classification? In addition to that, he's given us some live examples and shown how things can go wrong, despite everything appearing to be good in the design. So these are a few things which have to be kept in mind. On behalf of all of you and on behalf of the organizers, both from the TAI side and the NHDCL CTS, I would like to thank Dr. Zeidler for such an elaborate. You could make out his knowledge, the depth of his knowledge is fantastic. So once again, thank you very much, Doctor, for being with us, for giving us a very, very, I know in subject, we cannot cover it all. And if the need be, if the environment we need some very specific subjects to be run by you, we will invite you again to answer some of our because I must also tell you today that most of the team has come from our organization NHDCL, where they are undertaking very large number of tunnels. So there are a lot of lurking questions in the minds of our professionals. So we will, as the time goes by, good that we have connected with you. So we'll get you on board to answer some of those questions. Thank you. Thank you, ladies and gentlemen, for connecting and for being here. All the very best. Thank you very much.
Thank you for the opportunity. Thank you for the opportunity to everybody and for listening in.
Dr. Zeidler, can you please share your presentation with all of us?
I've sent the presentation to the organizers. They can share it with you.
Yes, we will be going to share.
Thank you.
Yes, please tell them that we will share.
Yes, we will be going to share to all the attendees the presentation.
Thank you so much.
Thank you. God bless.
Thank you again and have a good rest of the day. A good evening, actually. Thank you. Bye-bye.
Okay. Bye-bye.
Thank you, sir.